Hey everyone, so we're jumping into a really cool paper today, one that takes a shot at a foundational idea in AI. You've probably heard of the groundbreaking paper, Attention is All You Need. It basically kicked off the whole modern AI revolution. But what if that's not quite right? What if attention isn't the thing we need? Let's get into it.
So this is the big question the paper throws out there, and it's a bold one. We're talking about a direct challenge to the very engine that runs pretty much every AI model you can think of. GPT, Gemini, you name it. Is this giant messy web of connections really the best we can do? Is it the only way?
All right, so to really get why that question is so gutsy, we first have to appreciate just how dominant attention has become. I mean, for the last few years, it's been the king. It's the engine behind everything.
So what is self-attention? Well, in a nutshell, it's a mechanism that lets a model look at an entire sentence all at once. For any given word, it can weigh the importance of every single other word. It's how models get context, right? But here's the catch. This look at everything all the time strategy creates a system that's so incredibly complicated that it's basically a black box. We know it works, but understanding how is a whole other story.
And that leads us straight to the main problem this paper tackles: interpretability. Or, the lack of it. It's his whole black box issue. These models are amazing, but figuring out why they make the choices they do, it's next to impossible. And this paper points the finger directly at self-attention as the culprit.
The paper has a specific name for this problem: tensor lifting. Okay, so what does that mean? Imagine each word in a sentence is just a simple point. What attention does is it lifts all of those points into this ridiculously huge, high-dimensional space. Why? Just so it can map out the connection between every single possible pair of words. This creates this monstrous data structure, a tensor, that's just a mess to try and understand.
And the paper's author, Zhang Chong, nails it with this quote. He says this whole tensor lifting process is mathematically non-traceable. I mean, what that really means is you can't follow the logic. When you have millions of these connections being calculated for every pair of words, and that's happening over and over again in dozens of layers, well, you totally lose the plot. There's no way to trace the model's reasoning from point A to point B.
Okay, so to really appreciate what this paper is proposing as an alternative, we need to get our hands a little dirty. Let's do a quick tutorial on how self-attention actually works under the hood. So the core idea, like we said, is this massive web of connections. Every single word gets to look at every other word all at the same time. Think of a simple sentence. The cat sat on the mat. For the word sat, attention lets it look at cat to know who sat, and it looks at mat to know where they sat. It's a total free-for-all of information, building up context from all directions at once.
So how does it do this? Well, it basically boils down to 3 steps. First, for every single word, the model generates 3 new vectors: a query, a key, and a value. You can think of it like this. The query is you asking a question. The keys are like the titles of all the books in a library. Then, step 2, you take your question, the query, and you compare it to all the book titles, the keys, to see which ones are a good match. That match gets a score. And finally, step 3, you use those scores to decide how much of each book's content, the values, you're going to read. You blend them all together to get a really rich answer for your original work.
Okay, so that's the established way of doing things. It's powerful, but it's a mess. So what's the alternative? Well, this is where the paper gets really interesting. It says, what if we just threw out that whole chaotic web? Let's try something totally different. A clean, structured, geometric approach. And that's where we meet this new idea called Grassmann flows. And this really gets to the heart of the difference. Instead of that global, all-to-all web, Grassmann flows are all about looking at things locally. So instead of the word cat trying to figure out its relationship with every other word in the whole document, it just looks at its neighbors, like the right before it and sat right after it. It's like building a chain link by link instead of trying to build an entire spider web all at once. So how does this actually work in practice? It's pretty clever. First, it simplifies things. Then it takes a local pair of words, say the and cat. Now, instead of just calculating a simple compatibility score between them, it does something much more geometric. Think about 2 points on a graph. You could just measure the distance between them, right? Or you could describe the angle or the slope of the line that connects them. This method does the second one. It encodes the relationship between the 2 words not as a number, but as a geometric object, like a little 2D plane representing their orientation to each other. Then it takes all these little geometric pieces and fuses them back into the main representation.
So meaning isn't a big soup of scores. It's built up from these clean, local geometric relationships. So here's the side-by-side. On one hand, you've got self-attention, global, brute force, creating this massive, messy tensor of weights. On the other hand, you have Grassmann flow. It's local, it's elegant, it's geometric. It's really a shift from thinking in terms of just raw computation to thinking about the underlying shape of the data. Okay, so this new idea sounds really elegant, right? But the million-dollar question is, does it actually work? Let's look at the results. And the results are pretty amazing. They ran it on a standard language understanding task, and check this out. The new Grassmann head actually edged out the standard transformer head. Now look, the difference is super small. We're talking fractions of a percent, but that's not the point. The point is that it worked, and it worked slightly better. This is a huge proof of concept. It shows there's another way to do this that isn't attention. But honestly, this might be the real showstopper: efficiency. See, self-attention has this huge problem. It scales quadratically. In plain English, if you double the length of your text, the amount of computation needed quadruples. It explodes. That's why current AIs struggle with really long books or documents. But the Grassmann approach? It scales linearly. You double the text, you double the computation. That's it. This is an absolutely game-changing advantage, especially as we want to process more and more information. So let's pull back for a second and think about what this all means. What we might be looking at here is a real turning point for AI. It's a potential shift away from just throwing more and more computing power at the problem, brute force, and moving towards something much more, well, elegant, a more geometric way of thinking.
And this final quote from the paper just says it all. What we fundamentally need is not attention as such, but a principled way for representations to move on the manifolds they inhabit. Okay, that sounds a bit academic, but the idea is profound. It's saying the goal isn't just to build bigger and bigger attention-based models. The real goal is to find the right language, the right math, to describe how ideas and concepts should connect and change. It's about principle, not just power. And so that leaves us with a really big question to chew on. For so long, the story of AI progress has been simple: bigger models, more data, more compute. But what if this paper is pointing to a different path? What if the next huge breakthrough isn't going to come from building a bigger data center, but from finding a more elegant equation? What if the future of AI is less about brute force and more about discovering the right geometry? Something to think about. Thanks for joining me.